Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on filter design. Okay, so for this video, I'm going to discuss the filter design specification. Okay, so it is very important to classify the performance of the filter. So hence this video, before we even start on the design of filter design, we need to know the specification in order to classify the performance of the filter. So basically, this will be the part A series discussion. Okay, so on my next video, part B series discussion, I will continue to discuss on the filter design specification. There are actually altogether 14 of them. So this video, I will start the discussion on the first 7 discussion of the design specification. Okay, so I will start by discuss what are the types of filter. In short, there are actually low pass, high pass, band pass, and band stop filter. Next, okay, I will define what is the center frequency of the filter, where to locate the cutoff frequency, how to know where is the stop band frequency. Next, the bandwidth of the filter. 6, the selectivity factor Q. Okay, so basically this selectivity factor Q has an inverse proportional relationship with bandwidth, which we are going to take a closer look later on. Last but not least, for this video, I will discuss the shape factor of the filter. So basically, this will be the objective of this video. This will be the part 2 series discussion on filter design. So guys, if you're keen to know more about filter design, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on filter design. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by pressing the like button. When more you guys actually help to press the like button, this video will have a better chances to reach out to a larger audience. So guys, help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for your support. So these are all the 14 filter design specification. Like I mentioned earlier on, I will kickstart this A series discussion on the first 7 filter design specification. I guess this is what we have discussed on my previous discussion on the part 1 series discussion. I have already discussed this, but in order to fully so-called discuss on the filter design specification, I need to go through this again. So the first one will be the types of filter. As I mentioned earlier on, we actually has 4 types of filter. First one is low pass filter, high pass filter, band pass filter, and band stop or band reject filter. What are they? They basically allow different frequency to pass or to stop. For example, for low pass filter, it actually allow low frequency to pass while they actually attenuate away the stop band at the high frequency. For high pass filter, it's actually a reverse process of low pass filter. As you can see from here, the low frequency will not be able to pass while the high frequency is actually allowed to pass. As for band pass filter, you actually specify a band to pass. For example, over here, you can see that this zone F1 all the way to F2, they will be under the pass band, which means that this band, all the component, all the signal will be able to pass, while the rest, they will be attenuate as much as possible. So this is for the band pass filter. As for the band stop or the band reject filter, for this, they actually specify a band to reject the signal. For example, when you actually want to remove a certain persistent noise, so what to do is to have a band stop filter to filter it, okay, exactly at that spot, then you actually successfully remove away the noise source. So basically, this is the objective of band stop, okay, is to specify a band to reject certain component. Okay, so basically, this is the first one, which is the types of filter. Next, okay, will be the center frequency. The center frequency of a filter is the midpoint. Okay, so for example, for the bandpass filter, this is what we call the midpoint. Okay, in a bandpass or bandstop. Okay, so the midpoint will be over here for bandstop filter, where the filter response is either maximum, as you can see from here, this is actually maximum for passband, or minimum, okay, as this point here is minimum for bandstop. So basically, this is a very simple definition of the center point. For example, for a bandpass filter, it will be at the midpoint. Okay, so for bandpass, it will be maximum value. As for bandstop, it will be the minimum value. Okay, so it represents the geometric means of the lower and upper cutoff frequency. Okay, as you can see from here, most of the time, okay, for example, for the bandpass filter, they are actually geometric symmetric. Okay, so what does this mean? Okay, for example, when I actually fold this into two, okay, you can see that they are exactly the same. Okay, so most of the time when we actually design bandpass filter, they are so-called the geometrically symmetric condition. Okay, so like I mentioned, they have identical, okay, from the left-hand side, from the right-hand side, they are actually identical. Okay, so the center frequency of a filter is sometimes also referred as geometric center. How can we actually obtain the cutoff frequency? Okay, so basically it's by this equation. This is the so-called the center frequency. I have the lower up cutoff frequency and the upper cutoff frequency, as you can see from here. This is the lower cutoff frequency. This is the upper cutoff frequency. So from this equation, you will be able to find the center frequency, okay, for this bandpass filter. Okay, so all this I will go more discussion, okay, on my next few series discussion on filter design. But this is the parameter number 2, how to locate the center frequency of a filter. Next, okay, will be the cutoff frequency. Okay, so this is very important, okay, especially for low pass filter and high pass filter. Let me define what is cutoff frequency first. The cutoff frequency of a filter is the frequency at which the signal power is reduced to half, okay, which is minus 3 dB of its maximum passband value. Okay, so what does this mean? So this is the maximum passband value. Okay, so when the signal actually reduced 3 dB below, okay, which is the half power. Okay, so basically this is where we locate the cutoff frequency. So this is what he mentioned over here. Okay, so it also marks the boundary between the pass band and the stop band. As you can see from here, the cut band actually also mark the pass band and the stop band. Okay, so basically this is the definition of cutoff frequency. Okay, so in short, for low pass filter, okay, basically they so-called are the transition between pass band and stop band. So all the frequency component over here will be able to pass. After the cutoff frequency, they want to remove as much as possible. Okay, so basically this is the cutoff frequency. Same for high pass filter. Once they exit this cutoff frequency, they will switch from stop band to pass band. Okay, so basically this is the definition of cutoff frequency. Next, okay, what is actually stop band frequency? The stop band frequency of a filter actually refers to the range of frequency that the filter is designed to attenuate away. Okay, so the key objective is they want to be significantly reduced or block that particular so-called frequency. The stop band is the frequency range where the filter response is below a specific attenuation level, for example, 20 or 30 dB below. Okay, so basically this is the stop band, okay, which I indicate over here. Okay, so the key thing is like, for example, I want to reduce, this is the maximum pass band value. I want to reduce, let's say 30 dB. Okay, so basically the key objective is I want to reduce by 30 dB at what frequency? Okay, so basically this is the definition of stop band. Okay, so this is for the bandpass filter. This is the maximum value I reduced by 30 dB. At what particular frequency I successfully reduce the signal by 30 dB. Okay, so this is another example for stop band. Okay, so because once we reach this stop band, we are very confident to classify them as stop band. As you can see from here, this is what we call the pass band. We have a period of transition. After that will be the stop band. So when we actually indicate the stop band frequency, so everything on this onward, for example, for this low pass filter, we are very sure that the signal will be fully so-called attenuate away or removed away. But on the transition period, okay, we are not that sure. Okay, this is a practical word. For filter, you actually has a so-called practical ways. We don't have a transition direct from pass band to stop band immediately. So therefore, this is a so-called reality, okay, of the filter design. We have a transition. We call this a skirt, okay, the skirt of a filter. So ideally, we want it to be as steep as possible. Okay, however, this may not be always possible. So therefore, we have this stop band to indicate whatever after this frequency, we are very, very confident that the signal will be so-called removed. Okay, so basically it's the same for this high-pass filter. Okay, so anything below the stop band frequency, we are very confident that it will be removed or attenuate away. Okay, so basically this is a definition for stop band frequency. Next, we come into the bandwidth. Okay, how to find the bandwidth of a filter? Okay, the bandwidth of a filter refers to the range of frequency that the filter is allowed to pass through with minimum attenuation. Okay, for example, for this bandpass filter, this is actually the bandwidth. The key objective is to allow this band to successfully pass through with little attenuation as much as possible. So this is basically the definition of the bandwidth of a filter. Okay, so it is typically defined as a difference between the upper and lower cutoff frequency. Okay, so what does this mean? Okay, so you see this is basically the so-called the lower cutoff frequency and the upper cutoff frequency for this bandpass filter. So this is what we define as the bandwidth of the filter. Okay, so for low pass filter and band pass, for high pass filter, it's not that clear direct here. Okay, but this bandwidth, typically, I will say that it's used to describe a band pass filter. Like I mentioned earlier on, this is the maximum point. So when I actually reduce by 3 dB on the left-hand side and also 3 dB on the right-hand side, this will be so-called defined by the bandwidth of the filter. Okay, so basically, this is the so-called the fifth discussion on the spec of the filter design. Okay, what is the bandwidth of the filter? Okay, so again, before I continue, guys, I'd like to urge you guys to help this channel by pressing the like button. If you have learned something from this video, okay, please consider to subscribe to this channel and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly take a close look. What is actually the selectivity factor Q of a bandpass filter? Like I mentioned earlier on, this is actually an inverse relationship with bandwidth. Okay, let's take a close look. What is actually selectivity factor? Okay, so the definition for selectivity factor is mentioned over here. The selectivity factor Q of a filter is actually a measure of its frequency selectivity, okay, indicating how sharp it can distinguish between the desired and undesired frequency. In short, this selectivity factor basically determines the skirt, if you still remember, the skirt of the bandpass filter, okay, how sharp they actually transit from pass band to stop band, for example, for this case here. So this is the definition for selectivity factor. It also known as the Q factor or Q. Okay, so basically it can be known as the selectivity factor, the quality factor, or simply just the Q, and is a key parameters in filter design, particularly in bandpass, okay, and also bandstop filter. Okay, so basically we will take a close look on this selectivity factor here. The quality factor Q of the resonator is used to describe the selectivity of the filter and can be characteristics as a frequency of the resonator divided by the bandwidth of the resonator. In short, this is actually the Q. Okay, so basically this is the center frequency for a bandpass filter. This is what we define the bandwidth. Okay, so if you still remember, it's actually the range from F2 to F1. So from here, you can see that Q has an inverse relationship with bandwidth. If we have a high Q, okay, then we need to have a low bandwidth. If we have a low Q, then we need to have a high bandwidth in order to achieve this. So therefore, because of this, like I mentioned earlier on, Q has an inverse proportional relationship with bandwidth. When Q is high, bandwidth is low. When Q is low, bandwidth is high. Okay, so we are going to take a close look how to determine the Q factor of a filter for a bandpass filter, for example. Okay, so I will give you two examples, two case study here. So from here, you can see that the first one, which is from 3.1 gigahertz all the way to 5.1 gigahertz. As for case 2, they have a wider so-called bandwidth from 3.1 all the way to 10.6. If you still remember how to calculate the F0, will be simply F1 multiplied by F2 square root. Then I will be able to obtain my F0, which is the center frequency of the bandpass filter. Same for this case here. But for this discussion, I'm going to concentrate on the Q, or the selectivity factor of the bandpass filter. Okay, so from here, I can easily compute my Q value here. Okay, so I just sub all the Q value. So basically from here, you can see that my Q is 2.05. While on the case 2 case here, okay, by having a larger bandwidth, okay, so basically you can see that my Q is lower. So from here, you can see that from the bandwidth, okay, so this is definitely has a higher bandwidth. You can see that I actually has a lower Q. And for case 1 here, okay, the bandwidth is so-called smaller, okay, then I actually has a higher Q. Okay, so basically this is what we call the selectivity. Just imagine this. Okay, so if we are very selective, okay, which means that we have a low Q. Okay, so if we are not that selective, not that so-called particular, the Q value will be higher. So this is actually, we are actually very picky. Okay, we want it to be quick transition, okay, from a high pass or from the stop band all the way to a pass band, etc. So basically, this is the selectivity factor of bandpass filter. Okay, so this is another example here. As you can see that this is actually Q equals to 1. You can see that they have a fairly big bandwidth. Okay, you can see that the skirt of the filter is also not that ideal at all. Okay, so when we actually increase the Q to 10, okay, you can see that the bandwidth can reduce drastically. And you can see that the skirt of the filter actually improve as compared to Q equals to 1. Okay, so again, when we actually increase the Q to 100, okay, definitely you can see that the skirt of the filter is more desired. Okay, so basically they have a higher selectivity from here, as you can see from here. Okay, so basically you can see that the bandwidth actually reduced drastically. Okay, so basically this is what is selectivity factor Q. Okay, so basically they have a inverse relationship with bandwidth. And you can see from here, when Q is equals to 1, you can see that the skirt is not steep at all. When we actually increase the so-called the Q, you can see that the skirt become more steep and more desired for this bandpass filter. So basically, in short, this is the 6th. Okay, I will have another slides to discuss on the selectivity factor here. Okay, so this is the series LC circuit and also the parallel LC circuit. The key reason why I put this over here is I want to highlight that to compute the Q for series and to compute the Q for parallel is a complete different equation, as you can see from here. Okay, so for this circuit Q, which is the total Q for this circuit, for the series is actually by this equation here. Okay, so basically is the reactance, okay, either the inductor or the capacitor over here over the combined so-called series resistor of the source and the load, as you can see from this equation here. So this is the so-called the total Q for the circuit. So this is the Q circuit for the parallel resonator. As you can see from here, they actually completely different from the equation from the series. The resistor is actually on top. For this series, the resistor is actually below. Okay, so over here, the resistor actually connected in parallel. So basically to compute is, I need to compute the resistor as parallel. So again, okay, basically for this reactance is basically either from the capacitor or the inductor, doesn't matter. They should have the same. Okay, let's take a close look on the behavior of the Q. So for example, when I actually want to have a high Q, okay, so in order to have high Q, what I need to do is, okay, I need to increase the reactance, okay, of either the capacitor or the inductor. How to increase the reactors here? For example, the L value can be increased. When I actually increase my L value, the reactance actually increase. However, for capacitor, I need to reduce my C value. When I actually reduce the C value, my reactance also increase. Okay, for resistor, I think it's quite obvious. I need to increase, okay, either the source resistor or the load resistor here. Coming to the parallel, okay, again, if I want to increase my Q, what I need to do is basically I need to increase my resistor. Okay, you can see that it's actually totally different from the series LC circuit here. Okay, so basically again, they are almost the same. Okay, but the key intention for this slide is to highlight, okay, the circuit Q to compute for series and parallel is totally different. Okay, so just to be very careful on this. Okay, so basically this is for the selectivity factor Q, okay, for series LC and also for the parallel LC circuit. Okay, coming to the last slide for the selectivity factor. Okay, so most of the time, the component are lossy. Okay, for example, the inductor, okay, it's not a perfect inductor. You have some form of loss, and we need to so-called classify this form of loss. Okay, so the loss can be represented as a resistor R loss in parallel, as you can see from here. Okay, why this is very important? Okay, for example, for a parallel resonator, once we have this loss here, okay, so the resistor, I need to consider this R loss. Let's say this R loss is a very small number. Okay, so when the resistor all connected in parallel, they are going to determine by the small number. So hence, the Q value may be affected. So when I actually incorporate this R loss inside on the circuit Q, okay, so the circuit Q most of the time will be lower. Okay, so basically this is the definition. Okay, because of the introduction, okay, since the component are lossy, they have some form of loss, and when the loss is quite low, this can be significantly impact the Q value, as you can see from this equation here. Okay, so the Q value actually depend on the source resistor. Okay, as you know from here. Okay, so now beside this source and load resistor, we also need to include the loss of the resistor and also the LC. So how can we actually resolve this? Okay, for example, okay, this is the circuit Q. We need to tackle the component Q. Okay, for example, for inductor, basically this is the component Q over here. Okay, so in short, okay, just to understand this fully, so in order to successfully, okay, to meet the performance of the bandpass filter, okay, we need to ensure that the component Q is many, many times bigger than the circuit Q. In order to achieve this, okay, so as a rule of thumb, okay, so basically the component Q must be at least 5 times or even all the way to 10 times bigger than the circuit Q. Okay, so in short, before you even can introduce this inductor into this resonator, okay, we need to compute the component Q. We need to ensure that the component Q must be at least 5 times better than the so-called circuit Q that we will be able to use in this circuit. Okay, so basically this is the last slide for the selectivity factor Q of a bandpass filter. Next, I'm going to discuss the shape factor. Okay, so let's come to the definition of the shape factor first. The shape factor, also known as the selectivity factor or the transition ratio of a filter, basically is a measure how steep the filter transit from the passband to the stop band. Okay, it's almost no same, okay, as a selectivity factor, but let me go through in a little bit more discussion on this, and you will know the key difference between shape factor and also the selectivity factor. Okay, so it is commonly used in the context of bandpass and bandstop filter, but can also apply to low pass and high pass filter. Okay, so what is this shape factor? Basically, this is the equation for the shape factor. It's the stop band bandwidth over the pass band bandwidth. Okay, for example, this is actually the S21 of a filter design here. Okay, so basically this is the definition of a pass band. This is the definition of a stop band. Okay, for example, I want to achieve 60 dB. Okay, from the maximum possible value from this pass band here, reduced by 60 dB. So this is where I classified my stop band. So from this equation here, okay, I need to have the frequency from this F4 minus F3, as you can see from here. I will have the stop band bandwidth. Then in order to achieve my pass band bandwidth is actually F2 minus F1, as you can see from this equation here. Then I will have my shape factor. Okay, so basically this is basically how to compute the shape factor. Basically, you can see that they actually also so-called quantify, okay, the skirt of the filter. Okay, so on my next slide, I will explain this. But this shape factor also describe the performance of the skirt of the filter. Okay, as you can see from this is actually the equation to compute the shape factor. Okay, so as the shape factor actually decrease, which means that this thing decrease, the filter end actually increase. Okay, so basically later on we will take a close look here. The selectivity is actually higher. Okay, so this is actually the shape factor. Coming to my last slides for the shape factor here. Okay, so basically, I just want to do a very quick comparison, okay, for two different cases of the filter design of a bandpass filter. So this is what we call a small shape factor. Okay, so if you still remember, the equation to compute is actually stop band bandwidth over the pass band bandwidth here. As you can see that the stop band bandwidth is very small for this case here. So this number will be small. So basically overall, they will actually has a smaller shape factor. For this case here, you can see that they are so-called gentle in terms of the skirt. Okay, so therefore, they actually has a bigger stop band bandwidth, okay, as compared to here. So therefore, this is actually bigger. So once this is bigger, we actually has a larger shape factor here. Okay, so if you take a close look, actually my intention is I keep my pass band the same for these two cases here. So basically, I just control my stop band bandwidth. Okay, so once I control my stop band bandwidth, I actually also control the skirt of the filter design. Okay, so with this, I hope you have a better understand what is actually the shape factor, what is the difference between shape factor and the selectivity factor Q. With this, I'd like to end my discussion. Okay, please help to like this video and also subscribe to this channel. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.